No, what did you mean with the column?
I didn't know if Elena's mic was clipped on too low.
Oh, I see.
Is it easier than holding?
Like up here, right?
Right.
That work?
Yeah, okay.
All right.
Right. Over some.
Okay, great. So the next talk is Areeb, who's going to talk about hidden Markov models and the Bayes filter in categorical probability. Thanks very much, Areeb. Oh, and if you're online and you can't hear us, just say and we'll switch mics.
Is there a way to get like the Zoom UI off the top of the screen? I always forget the keybind. Great. All right. Okay. I hope everyone can hear me. And this talk will be on hidden Markov models and the Bayes filter and categorical probability and Markov categories to be precise. So I'm Areeb Shah-Mohammed, and this is actually joint work with all of the authors up there. So Tobias Fritz, Andreas Klingler, Drew McNeely, Ewan Wang. Drew is actually here. So let's get started. So hidden Markov models, all right, as the name suggests, they're a type of statistical model, and they're used in a bunch of domains: sensor estimation, optimal control, decision theory. And the general idea is that, as the name suggests, there's some kind of a Markov chain in the background. So the idea is that you have a hidden system, which is a Markov chain, which means that the behavior at the next time step is going to be independent of all previous behaviors. It just depends on what the system's doing at the current time. And our Markov chains will be discrete. And now the hidden aspect of it is that we don't actually get to see the states, but what's actually there is a bunch of observations, which we sort of thinking is arising from these hidden states through noisy functions. So that sort of diagram, if you can see the mouse, then this diagram that I'm mousing over is sort of how people usually depict this kind of scenario. So you have your chain and you get observations. So just a bit of review. I guess we saw most of this notation already. The only difference is that I'll have our string diagrams vertically, so running from the bottom to the top. The unit, I just have this like curly I, and this is shorthand, like n in the square braces is just 0 to n. So yeah, a bit of review. We've already seen this, but just a lightning review is that you have a semi-Cartesian symmetric monoidal category. So the semi-Cartesian bit means that the monoidal unit is terminal. So in the terminology of the previous talk, that just means everything's total. And yeah, the idea again is that somehow these morphisms are random functions, and tensoring morphisms means you run the two random functions independently. And so a joint distribution is just taking values in a big tensor. And we saw some of these examples already, but I'll just go over them again so we know the names that I'll be using. So Finstock is what we call the Markov category that we use for finite probability. So the morphisms are now stochastic matrices. So you think of an entry f of y given x as a probability of this element x being sent to y. And so the matrix notation is nice because it turns out that stuff like tensoring corresponds to the tensor product of matrices, composition is matrix multiplication and the like. So that's sort of like a very prototypical example because yeah, it's probability. That's sort of what we're advertising ourselves as doing. But Markov categories can also take a very different flavor, which is, well, we call this FinSet multi, and the idea is that now we're just looking at multi-valued maps. So instead of a random function which sort of spits out a probability of some value being the output of an input, you just keep track of whether it's possible or not. So it's sort of similar to relations of the previous talk. And as far as the actual sort of like underlying machinery under the hood goes, it's very similar, except instead of looking at probabilities, you just think of like 0 and 1 as false and true. Oh, okay, I would have liked the other order, but the idea is that now all the arithmetic works out the same, but addition is sort of disjunction and multiplication is conjunction. And a third sort of example, going back to probability, is a bit more on the practical flavor. You get a Gaussian probability, where now your morphisms are like affine maps. So you sort of think of it as a linear operator, so some translation, but you also add some Gaussian noise. So it's like you have a deterministic well-behaved bit, which is given by a linear map, and you also have Gaussian noise parameterized by its mean and covariance. And well, again, we saw conditionals for quite a bit of the last talk, but we're using some notation here. So the idea is that if you have a morphism with two outputs and you condition with respect to say y, we'll denote it by just sort of like bending the wire back and putting a box around it. Now, I want to emphasize that the way we're doing this is just notation. Like, this has nothing to do with, say, like caps or something that one often sees in like other sort of approaches to Markov categories or categorical probability. It's, well, the notation is suggestive there, but as far as we're going to be concerned, this is just notation. But maybe a little bit of an illustrative example is what happens when you just have a state, because then it's like, okay, to figure out what the joint distribution of x and y is, well, you keep x, but you sort of like condition y, so you pull that back down and you condition it with, well, just the marginal onto y. And the point is that if you instance this in sort of the prototypical example of finite probability, you get very much the equation that you would expect from a conditional. Anyway, that was the bit of the review. So let's actually start with what we're here to do, which is encoding sort of like these classical statistical objects, Markov chains, and the like into Markov categories. So we'll work with a Markov category with conditionals throughout, and then we will say that a state is an n-step Markov chain. So it's going to be a joint distribution over these state spaces x0 to xn. And we think of this as an n-step Markov chain. So it's like you start at x0 and then you move on all the way up to xn. And you say that this big joint distribution is a Markov chain if, well, you can rewrite it as sort of starting with an initial state f0, and then you observe that, copy it, feed that into the first transition f1, observe that, and the like up to the final transition fn. So this is just like a space conserving notation. Like there's no real bending going on, that's just notation. But that's sort of the idea of what we're doing here. So the sanity check is that in the finite case, well, okay, the big joint distribution that you pull out is what you would expect from a Markov chain in the classical sense. And the nice thing is that even though we just have this one uniform sort of description, thanks to the fact that there are so many varied examples of Markov categories, you get a very different flavor when you, say, look at a more possibilistic case of multi-valued function. So now we're not keeping track of probabilities, we're just keeping track on whether something's an output or not. So what this is saying is you're really looking at whether this sort of sequence could be observed in the sense of maybe is it possible that x1 is an output of x0 and x2 is an output of x1 and so on. So what we see is that in this sort of possibilistic case, you sort of get more of an automaton-like behavior because you're not keeping track of what the actual probabilities are, just whether a transition is possible or not. So that was Markov chains, and we're going to have a very similar idea for moving from Markov chains to hidden Markov models. What we do now is that, okay, as promised, there's an underlying hidden chain. So that's sort of like the bottom part of this big diagram. But now you add these observations. So we're doing something very similar. We fix a final time, and we talk about n-step hidden Markov models having sort of like this underlying n-step chain. But at each step, we also have a copy that gets fed into an observation. And yeah. So again, so what happens then is that if you start marginalizing, which is just deleting all the copies that you're not marginalizing onto, so the underlying Markov chain would just be obtained by marginalizing onto the X components. The sort of sequence of observations, which is what you expect to be accessible in practice, is given by marginalizing onto the Y components. And yeah, that's that. One thing I would like to say is that so we're looking at n-step Markov chains so far, so finite time. Now, if you have some notion of an infinite tensor product, so you can like make sense of joint distributions of infinitely many variables, then you can of course extend that to just like some sort of like Markov chain or hidden Markov model in with time natural numbers or something. Right. So, okay. When you have a hidden Markov model, the idea is you have some hidden state and you have observations. Now, one thing that's pretty natural to do in this scenario is try to guess the hidden state given maybe the observation or more likely a history of observations. So it's like you have some sort of hidden Markov model running in the background, and at a certain time you have access to all the observations so far, and you're trying to get an idea of what the hidden state is. So in our setup, well, the natural thing to do is just, okay, you have all these hidden outputs, you have all these observations. Well, okay, you just marginalize onto the observation chain, but keep the last hidden output, the thing you're trying to estimate, and condition on the rest. So what this conditional is just doing is that, okay, you take the joint distribution of all the observations so far, the last hidden state, and you condition on the observations. So this can be rewritten in maybe a little more intuitive manner. What this means is that, okay, so if you have just the hidden chain, you keep track of the last state, the current time, and you also look at the observations. Well, that is equivalent to having all the observations and also plugging a copy of each of them into the Bayes filter at that time. So that's nice, but that's a definition. And in practice, it can be pretty hard to calculate because you've got this massive conditional. So we have a nice little recurrence that we can use to construct the Bayes filter at time t from the Bayes filter at the time t-1. And I'd like to thank Dario, who's also here, for suggesting this construction to us. But the idea here is that, okay, you have your best estimate at time t-1. Well, okay, then you just apply the transition to that, and you get a sort of prior. You look at what the observation might be with that, and then you condition on that with the observation that you actually have. So I guess that's intuitive enough, and you can show that, yes, this does actually produce a valid next Bayes filter. So that's all. That's nice. It's sort of a recursive way. And another thing is that this is still a bit sort of parametric in the sense that, okay, we haven't really plugged in any observations yet. We've just talked about them possibly happening. Well, what we do is, like in the last talk, I guess, you can sort of think of a deterministic state as a kind of a delta distribution picking out an exact point. So our observations we will model as these deterministic states. So the idea is that you take this Bayes filter, and then you just plug in a bunch of independent deterministic states as the observations. So this also has a similar recurrence, which looks like this. So we're doing a very similar thing where we get a prior, but this prior now has all the previous observations in it already. We transition, observe, and condition. And the nice thing is that sort of the way you've written this is that you could imagine that maybe you're doing this kind of estimation in real time. So as you obtain the observations, you're simultaneously just running this sort of like recursive process and getting the estimation. So you have an estimate, then the next observation pops in, and you just do this quick calculation to update. So again, in well, the finite case, you get the expected formula. Again, you get this sort of like Bayes rule phenomenon. This is just shorthand. I'm just using this bold P as probability, but it's what you would expect. And again, you get a very different flavor from just shifting to another Markov category. So in the multi-valued maps case, this is sort of just doing two checks. So the idea is that you have some kind of non-deterministic automaton running in the background, quote unquote. So you have a sort of guess of whether the state at the previous time was observable or not, and you also do a check of whether you could get your current guess from the previous guess, and also if that's compatible with the observation that you see right now. So you're sort of just doing your best guess based on the structure of the machine itself, and also checking that, okay, this is a valid hidden state that would produce the observation that I actually have in front of me. And a more like important example in practice, I suppose, is the Kalman filter. So if you instance the base filter in this Gaussian category of, well, linear maps plus noise, you recover the Kalman filter, which is nice. It's been used historically quite a lot, particularly because it has these very explicit formulae in terms of just like matrix operations for updating the mean and the covariance of the distributions. And it turns out that if you just look at what our recursive construction is doing and translate that into Gauss, you do get these formulae back. And so this is kind of just a quick slide into the further stuff. So the thing is that if you have what is called a representable Markov category, so that's intuitively a Markov category where there's a notion of distribution object, you can go a bit further in the sense that so the sharp of a morphism is sort of a deterministic morphism that encodes the same data, but instead of spitting out a random value, it just spits out the distribution of this random value. So it's sort of the same information in a different form. And if you have this, you can literally write the update map as taking the deterministic counterpart of this conditional. So you're not like repeatedly composing and conditioning, you're just forming some conditional once and for all and then just composing. And it turns out that you can show that these deterministic counterparts themselves will form a Markov chain. I won't go into too much detail unless anybody has questions or we have time, but I just wanted to throw this out there. So I guess now's a good time for questions, if anybody has it. Yeah, if I have more time, I can talk about more stuff. But
Okay. So are there any questions just now?
Hi, thank you for the talk. What is SAMP?
right, okay, so that's on the first hidden slide. But right, that's what I meant. But so the idea is that in a representable Markov category, you have sort of internal distribution objects. So if you have an object X, what we've denoted by Px is going to represent the distributions, and the idea is that SAMP is then a morphism from distributions over an object to an object itself, and that's just sampling from this distribution. So the idea is that if you go to a deterministic counterpart, then to get the original morphism back, you just get this sort of like true, not random function that spits out a distribution and samples from it.
Okay, thank you.
James.
Like on the second or third to last slide, you talked about 3 different settings. Oh, one more. Yeah, this one. So in Finstock, like we get this formula. In FinSet multi, we have this like local check. And in Gaussian distributions, we get the Kalman filter.
Right.
Does this formula for IBF is not the Viterbi algorithm. The Viterbi algorithm is the only thing I know about HMMs, is that there's an algorithm called the Viterbi algorithm that everyone uses.
Okay,
Is that something we could recover from this formula?
The name is new to me, but this is, well, as far as the formula goes, yeah, it's pretty classical. So
Okay, this is the classical formula.
the name is new to me. I'm sorry.
Okay, and then the second bullet point here is like it seems super local. You're not backtracking in any way. Is that baked into how IBF is defined? Because the Kalman filter also doesn't backtrack.
Right.
That
Yes.
seems important. Could you say something more about that?
Right. So that was actually a little bit surprising to us, and it is sort of like a consequence of, well, I guess everything's a consequence of the definitions, but more more interesting. What we were surprised by was sort of the second part here, where somehow these filters or their deterministic counterparts are Markovian. So somehow to us, the interpretation of that was kind of what you said, in the sense that somehow to get the next best guess, you're not really looking much further than the previous best guess.
So that output is Markovian. Like the HMM model is Markovian,
Yes.
and the algorithm for filtering is always Markovian. And that's a consequence of these recursive definitions.
So I can be a bit more explicit, and again, on more of the secret slides. But so this is the sort of process. So it's like you have all the filters, and you just produce your observations and feed a copy of each observation into the filters. And this chain you can show is Markov with precisely these transition functions.
Yeah, I think this is really exciting work and great way of casting like classical engineering things in ACT. So I think being able to see, oh, all these filtering algorithms are just Bayes filter in the category of X. That's really exciting. So I just want to highlight that.
Yeah, thanks. It was actually like somewhat surprising to us. Like there's a lot of like apocryphal, if I'm pronouncing that right, data in. So for instance, this Markovian property was quite a shock to us, but we spoke to somebody and then they were like, yeah, that's a known consequence of tower properties. And they were like, oh, okay, so this is well known, or to someone at least.
It's known at the level of vibes. It's good to see it, formal. It's good.
Yeah, thanks.
Can I, on a related, well, I don't know if it's related. Does it connect to sequential Monte Carlo methods? Do you know that?
No, not in detail, no, sorry.
Okay.
Can I ask a question online?
Right?
Yeah. Could you give a example of this sampling morphism in some concrete categories? I like the intuition for this.
Right. So the trick here is that sampling is not deterministic. It's not really a function. It's a random function. So for example, in the concrete category of like finite probability, sampling would take a distribution and produce a random value according to that distribution. So if you take like two elements, right? So you would take a distribution on 0 and 1, and the probability of that distribution being sent to 0 would be the sort of value of 0 on that distribution. It would be the probability that that distribution itself tells you. So I guess it's probably easier written out, but I can't really do that here. But does that help answer your question?
Yeah, thanks.
Okay, thanks for the talk. Have you tried instantiating this construction in other categories than Gauss and maybe modifying it a bit to get different flavors of Kalman filter?
No, not really so many variations in the linear case. We've tried just doing more classical, like the Borel case, more continuous cases, and then you get similar filters. But
are they like known in the literature, like unscented Kalman filters, stuff like that?
Drew, do you want to say something?
Yeah, I can say a little bit.
Hi. So I think a big problem is that a lot of these other different flavors of the Kalman filter rely on approximation of distributions, which is kind of problematic because when you propagate distributions and approximate them and truncate higher order moments and stuff, you lose associativity and other things. So yeah, I have a lot of opinions, or I've been thinking about it a lot, but we can talk later maybe.
Thanks. Where are we now? Let's see.
Thank you. So I just curious to ask, is this method have a requirement like, does the state model has to be linear, or does the noise has to be normal distribution? Because your example have been, yeah, it's like a common filter or hidden Markov model. So yeah, basically my question is like, does this is okay works for like the sequential Monte Carlo, also named the particle filtering?
Right, so the main requirement is just that it needs to boil down to an actual Markov category. I don't think that we were able to work particle filtering into a Markov category, and I'm not sure about sequential Monte Carlo. So.
Okay, oh, thank you.
Thanks for the talk. Does SAMP give you some kind of like factorization system on the morphisms of the category where I can always go from X to some probability distribution over X and then do so that's like the deterministic part, and then SAMP is like the stochastic part, and I can factor any, X to Y morphism that way?
Yes, that's correct.
Okay, cool, thanks.
Maybe it's not an orthogonal factorization.
So maybe I would add that, so a consequence of that is, so something like the finite case is not representable because the distributions on a finite object are not going to be finite in general.
Yeah.
Thank you for a very lucid talk. Could you comment on some of your future work? There's a lot of activity in classical extensions of classical hidden Markov models, like generalizations to autoregressive processes. And so how is your thinking going forward with all this wonderful work to extensions?
Yeah, so we are just in general interested in trying to extend just more of the theory of stochastic processes to Markov categories. I think so one thing that we do have as a hopeful long-term goal is trying to figure out a way to talk about the continuous case. So like all our stuff here was discrete. In fact, well, I think the stuff I talked about was just finite time. You can go to infinite discrete times with infinite products, but as far as trying to work with continuous stuff goes, we would have to try and implement more of, I guess, classical ergodic theory or results of that flavor into Markov categories. So that would be nice, the answer, but we also, I think, need to get more of, I guess, foundational material done with Markov categories.
Another quick question? Great. Well, thank you very much. We'll carry on talking on Zulip or in a coffee break. Yeah, thanks. It's coffee break time. Thank you.